Next chapter, rotation. A rotation is the turning of an object about a fixed point. The fixed point is called the center of rotation and does not change. The amount of turn or angular distance is called the angle of rotation. Consider an object moving along the circular path from A to B. O is the center of rotation. Theta is the angle of rotation. The distance OA is equal to the distance OB because it is the radius of the circular path. In the same way, geometric shapes can be rotated. A rotation is fully described by the direction of rotation, center of rotation, and the angle of rotation. The direction in which the hands of a clock turn is called clockwise, and the rotation in the opposite direction is anti-clockwise or counterclockwise. The angle of rotation in a clockwise rotation is negative, and it is positive in anti-clockwise rotation. So this is an anti-clockwise rotation, and the angle is therefore positive. This is a clockwise turn, and the angle is negative. And so in general, a rotation turns a shape. In this example, the triangle has been turned or rotated. Sometimes shapes are rotated just a few degrees, and in other times they may be rotated significantly. In this example, the triangle was rotated anti-clockwise or through a positive turn. Whenever a rotation occurs, the figure must retain its shape and size, and so the two figures are congruent. In a clock, the center about which the hands move does not change. And in the same way, the center of rotation does not change. If a figure is rotated all the way around back to where it started, this is called a revolution, and it's 360 degrees. Halfway around, it is 180 degrees. Notice that in these rotations, it doesn't matter whether the rotation is positive or negative. The image is mapped onto the same points, whether it's clockwise or anti-clockwise. When a figure is rotated exactly 180 degrees, it is said to have point symmetry because each point has a matching point and is the same distance, but in the opposite direction. To be able to rotate a shape, all you need to know is the angle and center of rotation. Of course, the angle will tell the direction of rotation. As the case may be, you might measure the angles or construct them if possible. So let's try and rotate triangle ABC 40 degrees anti-clockwise about the center of rotation O. Another way of saying that is a rotation of positive 40 degrees about O. We cannot construct 40 degrees, and so we will be forced to measure that. But we need the compass to measure the distance from the vertices to the center of rotation, because we will need the same equal distances from that center to the vertices of the image. The first thing is to draw a line from A to the center of rotation. We put this one aside first, and then take the protractor and measure 40 degrees in the anti-clockwise direction. Now rotate that so that the line OA matches the horizontal line on the protractor. Yup, there. 40 degrees is here. Remove the protractor and draw that line. Now I will take the compass there and measure this distance OA because I need the same distance on my new line. I'll mark the distance here, and that's A prime. Next, we go to B and rotate that point. Draw the line to O. I place the protractor now and measure 40 degrees in the anti-clockwise direction. That's now lined up, and 40 degrees is there. Remove the protractor and draw that line. I need this compass now. Measure OB and mark the same distance on the new line. That's B prime. Put that aside. And lastly, we do the same for C. Draw that line. Take the protractor and measure 40 degrees. Rotate that. 40 is here. Draw that new line. Measure the distance OC. And now take the same distance on the new line. And that's C prime. Now we join our new points to complete the figure. There you go. It looks clustered because the center of rotation was so close to the object and the angle of rotation wasn't that big. When you do constructions, make sure the pencil is sharp enough and do not draw thick lines. Now, in certain cases, you might be required to construct the angles in order to also test your construction prowess. Mostly, this will be rotations of 60 degrees and 90 degrees. And so let's do a rotation of positive 90 degrees about the center marked on the page. And sometimes these constructions may look slightly different from what you might have been used to. But the key thing is to understand the principle. For instance, in certain cases like bisecting lines, some people may draw complete circles instead of just arcs. It doesn't make any difference, never mind they don't even need the whole circle, just the intersection points. Okay? So back to our triangle. We take a ruler and join the first vertex to O. I want it long enough. Now, in the previous example, I was taking the distance from the vertex to the center of rotation and reproducing it on the new line. Here now, I will take that distance and then, using O as the center, draw a circle. And the reason I'm doing this is because any point on that circle is the same distance from O. And so wherever 90 degrees will fall, the new point will lie on that circle. And I will not have to measure the distance from O again. Got it? Good. We will now construct 90 degrees at O. So mark an arc. The other side. And an arc. Now draw that bisector. So from O, which is the anti-clockwise direction, it's from here to over here. See that? That's our point P prime. Now you get why we drew the circle. But you can even decide to measure the distances. I'm just using these two methods, so you choose which one works best for you. We will do the same for the other points here. Join Q to O. We use green. Next is to measure that distance QO. Not yet. There. That's okay. And draw the circle. We now bisect the line. First arc. The other side. Oops. Second arc. Draw that bisector now. Now you see, if this point rotates anti-clockwise, it will come here, and that's Q prime. And to our third point, take this away first. We join R to the center O. And then take that distance. It will be our radius. We come here and draw the circle. All right. Now we bisect the line. An arc to the other side. Over here, another arc. Finally, the bisector now. (90° counterclockwise). This point comes here, and that's R prime. Now I will simply join the 3 points. And this is the figure. And so the blue triangle has been rotated positive 90 degrees about the center of enlargement O to become the black triangle. Now let's do a clockwise rotation, and this time the center of rotation is actually one of the vertices. Recall we said that any point on the center of rotation does not change, so this point will not move. What else? Nothing. We start. Join the side to the center of rotation. Place the compass and take this distance. Draw the circle. Now we bisect the line. An arc to the other side. There. The other arc. And now draw the bisector. The rotation is 90 degrees. So this way was anti-clockwise. This way is clockwise. This point will come here. So M prime is there. We go to N. We draw the line. take this distance and draw the circle. Now bisect the line. I got to remove this one first. Mark an arc to the other side. Okay. Another arc. And the bisector now. This point, if it goes this way, it will be positive because it's counterclockwise. We want it this way. So N prime is right over here. And the first point is over here. That doesn't change. Now we join the 3 points. And we have our rotation. Excellent. And so much for that. That's how rotation works. Now I love this next part. As you can see on the screen, I have triangle ABC and its image after rotation. And below there, I have my slide indicating a rotation of 115 degrees positive. And using my slide, I can rotate it up to 360 degrees. And you see positive rotation is anti-clockwise. But as you may notice, there's no visible center of rotation. And this is deliberate because I want us to find it. I'm going to show you how to find the center of rotation, and I'm going to cheat a little because I'm going to use this program to do it for me. But I will still show you how to do the construction using a compass and a ruler. When you want to find the center of rotation, first thing you do is connect any 2 corresponding points, like A and A prime, and then draw a perpendicular bisector of that line. That line bisects the line A prime. We do the same for one other pair, like B and B prime. Find the perpendicular bisector, and where the 2 bisectors meet is the center of rotation. In this case, it is at 0.71. And you see, if you rotate the shape, that point don't move. I love this part. And of course, I could have joined C and C prime as well. And find the perpendicular bisector, and you see they meet at the same point. And now we have 3 perpendicular bisectors intersecting at the same point, 7,1, which is the center of rotation. Beautiful. Now, enough with cheating. Let's have one example and find the center of rotation without the software. This time we have a rectangle ABCD and a rotation of itself. Connect A to A prime and do the same with B and B prime. Those 2 are enough. Now I get the compass, and I'm going to construct the perpendicular bisector of A prime first. An arc down here, and another one up here. We move to the other vertex. An arc up here, and another one down here. Now we connect the intercepts. There. Now I know the center of rotation is somewhere on that line. We repeat the same for B prime. Open that to more than half. An arc down there and an arc up there. Move with the same radius to B and do the same. Arc and another arc. Great. We don't need the compass anymore. We just need to join the two intercepts. And now the two bisectors meet at 0.40, and that's the center of rotation. To find the angle of rotation, you join any two corresponding points to the center of rotation. A to O and then A prime to O. The angle between them is the angle of rotation. Direction: it's obvious that this figure was rotated anti-clockwise, and so it's positive 140 degrees. That's easy. You see, the thing about constructions, transformations, and graph work is that you need plenty of practice to improve on your speed, and don't forget neatness. Now, before I go, I want us to look at something called rotational symmetry. Now, when a plane figure is mapped onto itself under a rotation of angle theta, where theta is between 0 degrees and 360 degrees, it is said to have rotational symmetry, with the center of rotation being the same as the center of symmetry. In this figure, ABCD is a rectangle and has a center E. When the figure is rotated through 180 degrees about E, it fits onto itself. Another rotation of 180 degrees about E, and the rectangle assumes its initial position. The rectangle is said to have a rotational symmetry of order 2. The point E is the center of rotation. Any figure with a rotation symmetry of an even order is said to possess point symmetry. Consider the case of a square. If the square is rotated through 90 degrees about the center O, it fits onto itself. Another 90 degrees rotation and it fits onto itself again. In fact, a square will fit on itself 4 times through a rotation of 360 degrees. We say that the square has a rotational symmetry of order 4 about the center of symmetry. Now we look at rotational symmetry of solids. Consider this cube. When we rotate it about this axis for 360 degrees, we can see that the cube matches itself for 1, 2, 3, 4 times. With that, we can say that this axis is the axis of rotational symmetry of order 4. This cube has more than one axis of rotational symmetry. This is the second axis of rotational symmetry. When we rotate the cube about this axis, we can see that the cube matches itself for 1, 2, 3, 4 times. So this axis of symmetry has order 4. For the third axis of rotational symmetry, it has the order of 1, 2, 3, and 4. For the fourth axis, this axis has the order of 1, 2, 3. The fifth axis, this axis has the order of 1, 2, 3. For the sixth axis, this axis has order of 1, 2, and 3. The seventh axis, this axis has the order of 1, 2, and 3. For the eighth axis, it has order of 1, 2. For the ninth, the order is 1, 2. For the 10th one, this axis has the order of 1, 2. For the 11th axis, it has the order of 1, 2. For the 12th axis, it has the order of 1, 2. For the 13th axis, the order is 1, 2. And so this cube has a total of 13 axes of rotational symmetry.
The way we teach it in university and in high school as well, and colleges, is if you fall behind, you're in desperate trouble. That if you miss a class or miss an idea or don't do your homework, you go to the next class and the teacher assumes you know it, but it's like Greek to you. And so the biggest challenge is not falling behind, and the strategy is do whatever needs to be done so you don't fall behind. Seek help wherever you can find it, from students, from student help centers, from the teacher, from the teaching assistant, wherever you can get it. Because if you fall behind, it's like you're missing a floor in the building, you're missing a brick in the wall, and you just can't build the second floor without a good understanding of the first floor.